Okay, so we'll start today. Session is going to be on sequence models. Basically, we'll see some problems, assignment type problems in sequence models, and then I will briefly discuss backward through time, right, which is the way that recurrent neural networks are trained. And finally, I will go through a hands-on example of using an LSTM network to do sentiment analysis. Right? BPTT background time. Okay. Okay. So let's start with the first question. Uh, Very simple identification type question. We have to identify the types of applications where inputs are of fixed size and independent of each other, right? So these are the applications where you would not apply sequence models, where you would not apply recurrent models, sequence models. So, you know, look at the type of applications that you are seeing here and try to figure out which ones are suitable for sequence models and which ones are not suitable for sequence models. Okay, so So no, right? Because if you want to predict the sentiment of an individual, basically what you have to do is that uh, you have to read the uh, entire review, right? And that is basically a sequence, right? That is a review, a review is nothing but sequence of words uh, put together in sentence grammatical format, right? So to predict the sentiment of a movie review, you have to read, or at least you have to process the entire sequence that forms that review, which means you have to do sequence models, right? Same for C, which is trying to predict parts of speech, right? You have to read the sentence, you have to process the sentence. Word or autocomplete also the same thing. You have to process the sequence of characters that have come up until this point and then predict what the next characters are going to be, right? So the only option that does not actually involve a sequence is any kind of sequence of image classification, right? Image is basically just one kind of data point, and then you're trying to classify it, right? So there is no inherent ordering as such, but at least that was the way that that is thought about image classification, right? Uh, the community that the deep learning community is increasingly rethinking this old idea of image classification or rather the idea of images as being like single data points that are not sequences, right? And okay, it's not in this part, but uh, yeah, so we'll see it here. So the question is, which of the following are possible inputs to a sequence learning problem? And the basic idea is that in order to be an input to a sequence learning problem, this input, this whatever you see here, uh, the option that you choose is something that has to be mm, that's like something that can be modeled as a sequence of some other smaller uh, component parts, right? That's how you think about these things, right? So basically, if certain input has to be processed as a sequence, then it must be able to be modeled as a sequence, right? So the question is just which one of these typically deal with the sequence, uh, typically you think of as a sequence learning problem, right? And yeah, so this question is a little dated uh, since certain things that have become popular in recent times. But yeah, we'll consider them as well. Mm, try to carry on. Mm, uh, So in this example, or at least in the kind of older version of this, the answer that we have gone with is image, right? So image is the exclusion, which means that the others are things that you consider as sequences, right? And they very natural sequences, right? Text is a sequence of words, speech is a sequence of syllables or sounds, phonemes. Video is a sequence of image frames and so on and so forth. The one thing that you would not typically consider as a sequence is an image, right? But even that is changing in recent times, right? So as I mentioned here, with the popularization of vision transformers, right? So there is uh, transformer models that specifically work on image inputs, right? And the way that they think about the image basically is as a sequence of patches, right? So you have this kind of ordering that order the patches from like going from the top, build one kind of ribbon at the top, right? One of the where they put the patches, and then you come down, put the patches, so on and so forth, right? And in this way, you can basically create the entire image thinking of it as like a sequence of patches that you're going to place it, right? And then the way that you normally train this kind of networks is by uh, generating an image and then blanking out certain patches from that image and letting the network try to guess what those patches should be, right? And you train it through and you give this input to like a transformer network, and then the transformer network tries to fill in the gaps, right, and generate the image as it should have been. And that's how that's how people are kind of increasingly thinking of images also as patches. Of course, the problem with vision transformers is that uh, they are quite expensive, computationally expensive compared to the standard uh, like convolution based approaches of image processing, right? Computer vision, and uh, because of that, they are not used quite as much, right? Uh, so, but yeah, so these couple of questions that we dealt with just now, they are kind of they're kind of outdated a bit, right? But uh, even now, I would say the broad consensus is that you should not treat an image as a sequence. You should just treat an image as like a single data point, right? It's a large data point, but the idea is that there is no inherent order orderedness to the data that appears inside an image, right? So, like whatever appears at certain parts of the image, pixels of certain parts of the image is independent of what appears in the other parts, right? There is no ordering that goes on in that image formation, right? So this was about that. Uh, then once again, kind of similar question, right? But slightly more specific applications, right? So the question is, which of these applications do not belong to sequence learning approach? So once again, you have to identify which of these applications typically involve sequences, right? And the ones that do involve sequences, those are the ones where you require sequence learning approach, and the ones that do not involve sequences are the ones that where you will not require sequence learning approach, right? So here, so face recognition certainly is an application where you would not require sequence modeling, right? Because you're basically just looking at the image of a face and you're trying to match it with the identity of a person, right? So face recognition is one where you don't require sequences. But apart from this, everything else here actually does require sequences, right? Language translation is a example, right? You're basically translating one sequence to another sequence, right? So you translate a sequence of words in one language to a sequence of words in another language. That's language translation. Uh, Speech recognition is the same, like we discussed earlier. Speech is nothing but a sequence of syllables or names, the atomic parts of speech. Uh, and stock market prediction again is very heavily reliant on sequence modeling, right? Because you want to be able to predict the movement of the price depending on the historical movement of the prices, right? The one thing, but the other thing that is remaining is image captioning, uh, which you might think that it is not sequence modeling, but it depends on. But the important thing here, the important kind of distinction here that we have to make here is that I have mentioned image captioning and not image classification, right? So if this had been image classification, for example, like doing ImageNet, right? ImageNet challenge where we try to classify an image, something like that. So in that case, uh, it would not have been a sequence learning problem, but because it is captioning, you know, now it becomes a sequence learning problem, right? Because when you have to caption an image, you basically have to describe it, describe the image in like a sentence, right? And the only way that you can construct a sentence is by using a sequence learning model of some kind, right? So it could be recurrent neural network, it could be transformer, whatever, does not matter. But bottom line is that you need sequence learning model in order to captioning of any kind, right? So yeah, so these are, I mean, these are the two specifically mentioned, pointed out here because they are the ones that would have some confusion regarding them, right? So uh, yeah, so we consider a sentence completion application, right? So you type the words and then it tries to predict for the next word. Uh, yeah, I mean, the question is which of the following models is applicable for a use case like this, right? So is it fully connected feed-forward network, convolutional, recurrent, or deconvolutional? Deconvolutional is basically transposed convolutional uh, layers, which are very similar actually to convolutional layers, right? So yeah, so think about, uh, so the basic idea is that here you might realize that this is a sequence, right? We are trying to generate a sequence and identify which of these pictures actually performs sequence modeling. Uh, yeah, so recurrent neural networks obviously is the correct answer, right? Because recurrent neural networks actually perform sequence modeling, right? They have the history, the hidden state. In recurrent neural networks, the hidden state basically has the past history information, right? And that's how it kind of kind of remembers the context that has happened in the past, and then tries to generate the next like future content, future outputs, right? Or the present predictions for the present token. So yeah, so if you are trying to do an autocomplete model, obviously you would use a recurrent neural network, right? Alternatively, you could use a transformer-based network, but we're going to leave it out for today. We will discuss. I would actually discuss transformer-based transformer architectures in the next session, which is also the next session for this course that we're taking. So we'll go into some details about transformers in the next session, right? So we'll talk about that. So for today, we are going to limit our discussion to recurrent neural networks, right? In this, by 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 what, and by that I mean like LSTMs, recurrent neural networks, vanilla recurrent neural networks, LSTMs, things of that nature, right? So yeah, so here you have a typical vanilla recurrent neural network, and this format of this kind of network is often called as the unrolled form, right? Basically, you have unrolled the inputs and outputs in the time dimension, right? So you'll see here that there is the first input going in is x1, then x2, then x3, and x4, and you're generating similar y1, y2, y3, and y4, right? And the hidden state of this recurrent layer also has this S1, S2, S3, S4, right? And then you'll see that there is a connection going from S1 to S2, S2 to S3, S2 to S4, and so on. So the question here is, what is the dimension of U given that xi is p dimension and Si is q dimension and yi is r dimension, right? So U is basically the weight matrix that is connecting X and S, right? So think of that. Yeah, so this. So in this case, because you know the matrix U is basically connecting X to S, right? And because X is P dimension, S is Q dimension, then the matrix U must be of P by Q, right? So the correct answer is option A, right? So then moving on to a related problem, right? So here, of course, there are three different weight matrices. So we can go with all of them once, right? Next up is the weight matrix V, which is the output weight over here, right? Connects S to Y. S is Q dimension, Y is R dimension, and it's fairly straightforward to figure out triple dimensions of the weight matrix V. Obviously, since the V weight matrix is connecting S to Y, right? Uh, where S is Q dimension, Y is R dimension, then the dimension of V must be Q by R, right? So correct option is BQ by R is the matrix dimensions of matrix V, right? And then finally we come to the matrix W, which connects the previous uh, hidden state S to the current hidden state, previous hidden state S of, let's say, t minus 1 to the current hidden state S of t, right? So the question is that what are the dimensions of W? This is should be very straightforward. I don't even have to think about it. Um, Obviously, the answer is Q by Q, right? Because both because it's uh, connecting layers of hidden state variables, hidden state uh, mm, layers of the same dimension, right? S of t minus 1 also has q dimensions, S of t also has q dimensions, and so on. So it's always going to be a square matrix that is q by q cells, right? So that's what you have. And then, so I think this is the last question that we're going to see today. Basically, imagine that you have this sequence of uh, images that have been provided to you, right? And the sequence is of these poses in certain fashion, let's say. And the question is how, like, you have to identify the next pose that's going to come given certain sequence of poses, right? And the question here is, like, how will you do this, or you do this prediction? Uh, And the secret to understanding this is to understand that there are two modalities that are being considered here. Uh, One, of course, is that there are these images that you have to process, right? So you have to think of what is the most significant, suitable way to process images. And the other thing is that there is a sequence part of it, which is the sequence of poses, uh, and that is something that can only be processed by a recurrent neural network, right? And if you put both of them together, then you understand that whether you realize that kind of network that you need for something like this is a mixture of a CNN and recurrent network. Right? So you have the CNN with recurrent units. So with your sometime uh, GG building, third floor. Third floor. And uh, yeah, so basically you need the CNN to model and understand the images. And once you have understood the images, you need recurrent units to predict the next pose, right? And then if you are kind of, if you are doing like a image generation problem where you not only predict the next pose, but you also kind of generate an image for the next pose. Then the next pose prediction that the RNN will produce, that will go into some kind of like a generative network, like a GAN, where it then like a conditional GAN, let's say, and then the conditional GAN basically generates an image that uh, tries to match to the image of the next pose in the sequence, right? So, yeah, so that is this, and then okay, so that is the end of the questions. Okay, so yeah, so we have basically gone through all of the questions. But, uh, now we will see something interesting. This is like a small introduction into backprop through time, which is the technique that is typically used to train recurrent neural networks, right? And so to just okay, so here is RNN typical RNN layer, right? So we are going to deal with just one layer, and that will be in, right? Yeah. So this is typical RNN layer, right? This is a typical vanilla RNN layer, as it is as you mentioned. Of course, the more complicated, the more complicated uh, further development of an RNN typically are something like LSTM layer or a GRU layer, right? LSTM is long short-term memory, and GRU is gated recurrent units, so on and so forth, right? So typical, but so we will see the way that backprop through time actually operates to enable us to update the update the parameters of the current neural network, right? And the good thing is that if we understand the dynamics for this kind of a simple, basic vanilla recurrent neural network layer, then we can also like it just scales up to the more complicated LSTM layers or GRU layers. Essentially, the fundamental core idea is the same, right? It's just that there are a bunch of other operations that are happening, right? Where over here, the primary operation is very simple, right? So you have input going through this U matrix, right? So you got U times x of t. This is our input coming in, and we have the history, right? So history is represented by W times H of t minus 1. So W is the state transition kind of matrix, right? Connects the past, uh, connects the past to the present for the hidden hidden layer, right? Uh, yeah, and then so you have this, and then you apply the tanh activation function, which is typically what is used in recurrent neural networks, and then you get h of t, right? H of t is the hidden layer activation, and then finally you just have uh, optional, can have like an optional linear projection, which is v of v times h of t, which will give you y, right? So this is the basic temporal dynamics of a typical current layer, right? The reason we call it a temporal dynamics is because you have time in this as well, right? So you have h of t as a function of h of t minus 1 and x of t, right? And the graphical way to represent this is something like this, right? So you have x going through this U matrix, and h, the h going through this V matrix into y, and there is a W matrix which connects h to itself, right? Self connection. Okay. Now we come to the actually useful uh, representation of this network, right? Which is the unrolled representation, right? So if you unroll a one layer recurrent neural network in time, right? How does it look? So that is what we try to um, describe over here, right? And we'll see, of course, that we have, in fact, unrolled it through time, and then I have depicted every operation in this layer as like a separate node, right? So you have x0 is the first input going through u, you get ux0, right? Which is just u times x of 0. Then there is a tanh operation. Obviously, in the very first time step, there is no history term coming in. So it's purely this ux0 that goes in. So you do the tanh operation and get h of 0, and then you have another matrix multiplication with v of y of 0, right? For the next time step, x of 1 starts in the same way. X of 1 goes through this u weight matrix, you get ux of 1, which is again just u times x of 1. But here you now have like a history, so that history comes in. So history comes in through this weight matrix w, right? So you get w times h of 0, that adds on to ux of 1, right? So you get ux of 1 plus w times h of 0, and that whole thing goes through this tanh operation, right? So you get tanh, and after tanh you get h of 1, right? So this is the hidden layer activation at time step 1, and then with the v weight matrix you get y of 1, right? And then same thing continuously going on and on until the t minus 1 time step, which is in total t time steps going from 0, since I'm starting from 0 going to t minus 1. So this is what rolled RNN layer looks like in the forward pass, right? So this is nothing but the forward pass. And the one thing, the important thing you have to note here is that essentially what an RNN does is that it takes takes a particular input sequence and it generates an output sequence, right? So it takes this sequence of x t's, right? X0, X1, X2, X1, and it generates a output y t, so y0, y1, so on, and y of the capital T, right? So the sequence to sequence kind of operation that is happening, um, one after the obviously, right? So then now that we have described the forward pass aspect of this, uh, let's see how the backward pass works, right? So if we do interlink with one layer RNN and we try to visualize the backward pass flow, it's very interesting because essentially what you have to do, I mean, it's actually it's very simple actually once you have this kind of a visual representation of things happening, right? Because if you try to write the equations, you might get confused, you might get lost. Um, but because in equations are difficult to handle sometimes, right? But when you have a visual understanding, visual representation like this, things become simpler, right? And the basic idea is that your backward pass must flow in exactly the reverse direction uh, as all of your forward pass operations, right? So you will see here that for every forward pass arrow that we have a corresponding backward pass arrow in the reverse direction, right? And this backward pass arrow basically tells you how the gradient is going to flow in a network to generate the update values for all of these parameters, right? Parameters will be U, W, and V, right? So, and the other thing here is that I have also kind of side by side implied what kind of operation that will have to be performed by this backward pass in the same way that I had done it for the forward pass, right? So when you're doing a matrix multiplication, the forward pass, when you do the same thing in the backward pass, when you're trying to propagate the gradient of the error in the backward direction, what you need to do is multiply with the transpose of the original matrix, right? So in the forward pass, you are using uh, this V matrix to generate Y from H. In backward pass, you're going to use V transpose to generate uh, the gradient of H given the gradient of Y, right? So if you are given the gradient of the loss with respect to Y, if you are given the gradient of the loss with respect to Y at a certain time step, the way you get the gradient of the loss with respect to H at that same time step in this particular uh, relationship is that you multiply the gradient with respect to Y by this V transpose, and then we'll get the gradient that flows like this direction, right? Flows from Y towards H. Similarly, uh, you have, if in the forward pass you apply this tan H operation, in the backward pass you have to apply the gradient of the tan H operation, which is something, of course, I'm sure, but not simplify that. I mean, it does not matter much, right? It is sufficient to know that the gradient exists, and it's something that easily compute like a closed form uh, value of the gradient, right? So yeah, so tonnage, and then for all the weight matrix connections, like I said, in the backward pass, you just apply by just multiply by the transpose of the weight matrix. right? Because you're going in the reverse direction. So here is an interesting thing. So I would say what I would like to concentrate on is over here, right? Uh, the gradients with respect to this one time step, right? Because this is kind of interesting. Something interesting is happening, right? So here we have to compute the gradient with respect to every node that appears. And first thing is, let's say you have gradient with respect to y, then what we have to compute is a gradient with respect to h. And we notice here that the gradient with respect to h actually has two sources, right? So one source of the gradient is flowing uh, from the y of the same time step, right? So given the gradient with respect to y, we can compute the gradient with respect to h, right, by this relationship. And then the other uh, kind of flow of gradient is coming from here, right, which is very interesting, right? So we consider h of 0, you can see that one source of gradient with respect to h of 0 is going to come from ux of 1, right? uh, where this is basically where you had this w times h of 0 when you had added this up, right? So this gradient is going to come like this with this wt transpose, right? Essentially what is happening is that your gradient is coming in an anti-causal direction, right? So it is coming from the future and it is propagating towards the past, right? So it is coming from time step 1 and it is propagating towards time step 0, right? And it uh, is being accumulated at this h naught, right? uh, and then so this is the first equation. Then the second equation is basically gradient with respect to ux, which is nothing but gradient with respect to h multiplied by the gradient of time h, right? So you get over here, and then once you have the gradient with respect to these two nodes computed, basically you can compute the gradient with respect to every parameter that is present here, right? So with respect to u, with respect to w, with respect to v, and our BPTT description basically complete, right? And now what I will do is I will take I will just take these intuition that we have developed by looking at this figure, right? Uh, and we will try to apply it we will try to uh, describe it or explain it or put it in terms of equations, right? Because that's what you need ultimately if you actually want to compute the values of the gradients and the values of the parameter vectors. So yeah, like I said, uh, finally, temporal dynamics of the backward pass. Essentially, the temporal dynamics of the backward pass becomes almost exact kind of anti-causal um, anti-causal mirror image of the temporal dynamics of the forward pass, right? Where in the forward pass you had h of t depending on h of t minus 1 and uh, x of t. Here, h of t is going to, the gradient with respect to h of t is going to depend on the gradient with respect to y of t and the gradient with respect ux of t plus 1, right? because of because of this relation, right? Because of this gradient flow from the future to the past, right? so so gradient with respect to h of t can be divided into two parts. Essentially, one part of this is the gradient flow coming from the next layer, right? So remember, the next layer, if you compare uh, the h of t layer to y of t layer. So the y of t is the next layer compared to h of t. So there is one gradient flowing in that direction, right? So you get p of p transpose times gradient with respect to y of t, which is the gradient from the next layer. And then we have a gradient flow from the future, which is W transpose times gradient with respect to ux of t plus 1, right? This is one equation. The other equation is gradient with respect to ux of t is the gradient of the tan h, right? So tan h prime of h of t multiplied by the gradient with respect to h, right? So it's just this middle, right, arrow, right? Tan h prime multiplied by gradient with respect to h of t will give me gradient with respect to ux of t, right? And now that we have these two equations, we can compute the weight updates for all of the weights that we need to compute updates for, right? And the third idea, third like thing to note here is that if there are multiple recurrent layers stacked on top of each other, then essentially this gradient with respect to y will just be replaced by this tan h prime of h of t, right? Because the h of t will be connected to the next layer of the uh, to the next lower uh, uh, the, the next lower like RNN layer, yeah? So it will become the top, right? So yeah, so here uh, notific here what I used is delta delta x is gradient of the mass with respect to x, right? In the del L by del x, L is equal to mass, and that y of t, so this part depends on the loss function that you are going to use for your problem, right? So, uh, so yeah, so that is backward potential dynamics of the backward pass that we use for RNN networks, right? It's called backdrop through time because essentially you're going in this reverse temporal direction, right? You're going from future to past. So, so finally, is the yeah. So finally, we'll see a sentiment analysis example, right? So this is a TensorFlow uh, code that uses um, let's see, we see that as we go through. Okay, so yeah, so we are getting a couple of things over here. Uh, First is TensorFlow Hub, which is a collection of uh, models that are available on TensorFlow. Specifically, in this instance, going to use the uh, word embedding model from TensorFlow Hub, right? And TFDS is nothing but TensorFlow datasets, right? So we're going to use some particular datasets from TFDS. That means TensorFlow datasets is TFDS, TensorFlow Hub, specifically collection of models. Right. So first of all, we need to have a dataset to train things on, right? And what we're going to use is a dataset of IMDb reviews right? So these are reviews that we can put on IMDb, reviews of movies, especially specifically, right? And we're going to split it into a 80-20 split, right? So first 80% is train, and then the next 20% is the validation, and then there is a separate test set. Right. So yeah, so we get train data, validation data, and test data. And then so here we are basically loading the word embedding model, right? And we are loading this word embedding model from TensorFlow Hub, right? So Hub is, like I said, a collection of uh, of models that you can use, like open source models. And so there are multiple uh, embedding models that you can use. Basically, here we are using Wikiwords 250. So this is a 250 dimension embedding model trained on Wikipedia files. Right? That's why it's Wikiwords. And there are multiple variants of this 500 dimension embedding model, also 250 dimension, which is what we are using. So, so yeah, so let's get the 250 dimension embedding model loaded, right? So this embedding model, if you remember session 9, we talked about embedding models, right? We talked about predictive, uh, we talked about skip ram, continuous backup words, so on and so forth. So those are the embedding models that basically encode words into tense vectors, right? So yeah, we have 250 dimension embeddings, and there are some fun exercises that you can try here, right? Where you can test for semantic relatedness of words, right? So in this specific example, uh, we take uh, we take these four words, right? Actor, boy, uh, actress, and girl. Basic idea is that uh, actor is related to boy in kind of a similar way that actress would be related to girl, right? So if you take the vector for actor and subtract the vector for boy, right? And then add the vector for girl, we should land somewhere close to the vector for actress, right? Vice versa. So, okay, yeah, that's exactly what. So taking actor, subtracting boy, right, this, and adding girl, right? And here, yeah, so we run this and find that what you kind of end up with, right? So the distance between um, this trial vector and the vector for actress is quite low, right? So it's 0.2 is the distance, right? And so this kind of shows things like semantic relatedness in the sense that so we can try something also. But, okay, we'll see this later. Uh, but yeah, so you can think of other examples as well, right? And try to see if they work out. You can see, you can try king, and you can try with king and queen, right? Right, so have king, queen versus woman. You can see, you can try to see what happens here. Yeah, I mean, it's not that great, but uh, whatever. right? It doesn't always work out, right? It works out for some examples. Yeah. So then we come to the network definition, right? And here things are pretty simple. So we take this 250 dimension embeddings, and then we use certain network architectures, right? So this architecture is input to a couple of LSTM layers to a dense layer value, which is like a linear layer with a value uh, activation function, and finally an output, which is just one singular value, right? Because we just want to uh, say if the sentiment is positive or negative, right? Similarly, you can input the GRE, couple of GRE layers, gated recurrent units, and yeah. So the basic idea is like this. So the model by default that I have here is the one that uses a couple of GRU layers, and we're using KRS sequential, which is a very convenient way to build models, right? So you just call model.add, then set it whatever layer you need to add, right? So the first layer is input layer, 250 dimensions. The next layer is a GRU layer, 32 dimensions. Uh, you want return sequences equal to true because you want all of the outputs, right? Because the next layer is also a GRU layer. Then third layer is another GRU layer with 64 units, and then finally fourth layer is a dense layer with 128 outputs, and then the final layer is a dense layer with one, right? This one has a value activation function. Final one does not have any activation function. So yeah, so we have a couple of GRUs. So here, since we don't activate return sequences, essentially what it will return is just the final output of the hidden state, right? So you just get one output per batch, or rather one output per sequence. So yeah, so let's do this and see the model summary. Yeah, so here is an interesting, uh, interesting thing facet. Um, Basic idea. So here you might see parameter numbers, try to understand, try to figure out what's going on. And basically what is going on here is that this GRU layer, it has three um, weight matrices, right? And the three weight matrices essentially the input to those weight matrices is the concatenation of the input and the hidden state, right? So the size of the input is 250 plus 32, so 282, and the size of the output of those weight matrices obviously is going to be 32, right? So each of those weight matrix is of size 282 times 32, and then three of them, so we get some 27,000 something number of uh, uh, parameters, 27,072 parameters specifically, and uh, rest of the parameters are essentially the bias vectors, right? So we have bias vectors for all of these um, internal, you know, etc. Right? So at those biases, we'll get this number, right? And then, so this is the first one. And the second one, of course, now our input dimension for the weight matrices is 96, right? The output dimension is 64. So just here, 64, we get 13,400 something, which is just this minus the biases and stuff, right? So that's the GRUs. And then there is a dense layer. Dense layer is simple, right? Dense layer is just 64 by 128, and then add the biases. Finally, there is a dense final dense layer, which is 129, which is 128 by 1 plus 1 bias, right? Then, yeah, so here, so this part is a little involved, and go through the whole thing. So first thing you have to decide here is we have to set the size of inputs that we are going to process for the training, right? So size here, so this size refers to the sequence length that we are going to process. And then, yeah, so then we generate, so this is a matrix of zeros of the size length of trained data, so the total number of batches that we have multiplied by the size, rather total number of samples multiplied by size, which is 150 we have set, and 250 is the number of dimensions of the embedding, right? And the trained labels is just size of the trained data, right? That's label is either 1 or 0. And embedding, PG embedding, so this is kind of this is padding, right? And then we go through the entire trained data, right? And we apply some processing to it. So the first processing that we apply is so this RE is regex-based processing, right? So it applies this processing. Basically, it removes all spaces, commas, things like that, right? Punctuations, basically, and it generates the words as like separate tokens, right? And then you put everything to lowercase, right? Because you don't random uppercase letters, right? And then you call the hub layer, which is our embedding layer. Right earlier, we call the hub layer with train embedding. I mean, we call the hub layer with this bunch strip list, uh, and call it as the trade embedding, right? So we split them by spaces and get the words, and then pass the words with embedding layer, get all of the embeddings that we need, and then we uh, pad them, right? So if the length of the sequence is less than 150, right? So we set the size is 150. If the length of the sequence is less than 150, then we place uh, the sequence inside this padded, and rest of the padding we just leave it as zeros, I guess. Uh, yeah. And then in case, I mean, if it is greater than 150, obviously you're going to truncate it to 150 tokens, right? And then train labels, yeah, so we generate string labels as well. So this is a processing, pre-processing rather, of the text that is present in the dataset, right? And then we run the training loop, right? So from each levels, sorry, it's not the training loop. This is the same processing, but for the validation set. So apply the same processing in the validation set. So let's run this. It's going to take a little bit of time. Mm, so here you can see that the training dataset has been processed, right? Mm, we have basically generated, so there are 20,000 samples, 20,000 review examples, right? And out of those, we have generated 150 token length examples out of it, right? So some of these reviews will obviously would have been longer than 150 words. Some of these reviews would have been shorter than 150 words, but we have kind of created a uniform, like uniform token, uniform sequence length of 150 words. And the reason that we do this is because it helps training to be faster, right? So you want kind of a fixed values for this. Typically speaking, of course, I mean, this is especially true for TensorFlow, especially for older version of TensorFlow. Nowadays, you would not necessarily do this. Right? Nowadays, what you would do, typically, especially specifically if you're using, let's say, PyTorch, um, right, is that you would generate the batch. For every batch that you generate, you have a different length of the sequence, and then you would use that to train your model. For that batch, it would run for more number of steps. For if there are more number of maximum number of tokens in a particular batch, you will run for more steps. If there are fewer number of tokens, it will run for fewer number of steps and so on. Right, but in the older kind of the older way to do this would be something like this, right? So you set like a uniform standard sequence. Okay, so and, and similarly there are 5,000 in the validation, and then there's nothing left to do but just train the model, right? So we just call model fit, pass the train embeddings, which is which are these, right? And the train levels, which are these. And we're running it for we're running it with a batch size of 10, right? Which is why you're getting 2,000, right? There are 20,000 total samples with a batch size of 10. There are 2,000. It's gonna run for 2,000 batches. Then for 5 epochs, we have set validation data. So we have these validation encodings and validation labels. So that's first epoch done, and you can see the accuracy, right? So in this case, since this is a sentiment analysis, you're basically looking for just two types of sentiments, right? It's either positive or negative, right? So at a baseline, you would expect even like a random model to get it right about half of the time, given that, of course, you know, positive sentiment is kind of equally uh, prevalent as negative sentiment. In that case, you get uh, something like that. But yeah, so then you can see model is improving. So it starts off with that random kind of accuracy, and now it has gone up to almost 80%, I guess. 78 or something. The training, and I believe it was 80% is the validation. It has crossed 80% training. See, right? So this is also like a good sign, right? Because validation loss is lower than the training loss. Validation accuracy is higher than the training accuracy, which means that model is generalizing well, right? So it is overfitting. Okay. But yeah, it's kind of parts just comes up sometimes. So gonna be done with this. So, uh, yeah, so one of the problems that I have been facing with this particular demonstration is the fact that I had to reduce this sequence length to 150. Um, Earlier, the collab used to be much more permissive, and I could train like with sequence length of much higher sequence length, 200 to 50, like 350 even. But the problem, and if you train with him higher, longer sequence length, obviously, one will going to perform it, right? But because now I'm forced to reduce this, right? Because memory has become kind of strict. Yeah, yeah. RAM has been shut up, right? Something, some high value, I guess. If I had used longer sequence length, it would have crossed the limit, and then, right? Because the program would have crashed, and then I would have no choice but to reduce the sequence length again. So, yeah, so what can you do? You're going to have to work with limitations that are permitted. Of course, you can get around this by not doing this processing uh, in bulk. So if you don't store these train embeddings, what you can do is that in when you're running the fit, you can generate the train embeddings on the fly per batch. In that case, will not be severely limited by uh, the uh, by the memory boundaries. But this is an older code. Ideally, do it with PyTorch. Have all of those kind of uh, like better ways to run right available to us. But we do with what we do, and then so this is the fun part. Here we are going to train. So we are going to test this model, right? And this is so we are going to test it on this on these reviews, right? First review is yeah. So the first review. So this is a movie review. So this was whole Netflix movie that had come currently too. And that's not important. Essentially, what is important is the fact that you can write positive and negative reviews for this movie, right? For any movie, right? And you can test it out, right? So this one, for example, this is obviously a positive review, right? Saying that it is good, it's good, and so on. And this, uh, yeah, so you get the output that sentiment is positive, right? Which is what you expect. Then, if we this, right? So now we have two types of reviews for the same movie, right? So it's the same movie, but second review is negative. First, whereas first was positive, and you can test both of them. So it will say that it can identify, clear cut case. So first review is positive, second review is negative. Network is identified properly, right? Um, so that's fine. This is what it has been trained to do actually, right? Because we have been training it on IMDb reviews, which are movie reviews. But the interesting thing, of course, is the fact that this, in fact, generalizes even beyond movie reviews, right? So here are, so these are Amazon product reviews, and I did not write them. these I have pulled directly from Amazon website. You can also pull similar other you know, reviews from their website and test it out. So the first one is a negative review, right? So yeah, so you get all kinds of negative experiences. Then you run it, you get sentiment is negative, right? And then second one is a positive review, like for some TV, run it and you get sentiment is positive, right? So this is kind of interesting uh, development. Of course, uh, if the model was well trained, this is something that you would expect from it, right? Because the idea of a negative or positive sentiment is kind of general, right? It is not something that is specifically limited to the domain of movie reviews or product reviews, right? The idea of a negative, of positive or negative sentiment, if you train on one kinds of reviews, it should be able to generalize to other kinds of reviews as well, right? Because they have uh, shared characteristics. And in this case, you do in fact see that uh, the trading carries over very well. It generalizes quite well to things that are out of the training distribution. Right? So yeah, so with that, I think today's session is kind of over. If you have questions, you can ask. Otherwise, yeah, you are free to leave.